Hello, everybody. My name is Hans Conrad, and I'm the CEO and founder of the company PROMECON. I'm very happy to be here today in Stockholm at this steel conference, and I hope that we'll have something interesting for you to look at and to learn about our measurement technology. So let's start right away. Just share my screen with you. All right. Today, I would like to talk about our infrared measurement technology to measure process gases. Our company has been active in measuring process gas in quite a few industries, including the cement industry, the power industry, waste to energy, but also the smelter business, non-ferrous, and of course, steel. Steel making is quite demanding from the measurement perspective, because of high temperatures and also the huge amount of dust carried with the process gas. But this is what we have been specializing in for the past 25 years. So let me show you a little bit about our today's topics. Our main products that we have at PROMECON are really around the gas flow of process gases. And when I say process gas, I mean right in the process of the smelter bath, out a boiler or a heat exchanger. So we don't measure gases after they've been cleaned and they're nice and cold, but we measure gases when they're hot and when they're dusty. And we do so with a digital measurement method that allows for a drift-free measurement of a long time. And when we say over a long time, we mean years, right? So one big pillar of our product line is correlation-based gas velocity measurement. We also have developed over the years microwave-based pneumatic solid transport measurement. So, for example, pulverized fuel, pulverized coal or biomass, or other materials that are conveyed in a lean phase conveying system. We have also developed a microwave-based unburned carbon measurement for combustion processes of solids, as well as a stack emission measurement. And when I say stack emission, I mean the flow of process gas through the stack. All very complicated and much more difficult than it seems. Most of the measurements in the industry and also on the stack struggle with accuracy and drift stability. Our measurements do not do that. Our main focus is on digital measurement in the process, and today I would like to specially talk about a measurement at the outlet of an electric arc furnace or a converter, which is the focus of today's presentation. But let's first have a look a little bit at where we are. I've picked out three industries that actually have become three important markets for us. There's more industries that we serve, but for the three here, power stations, steel plants, and cement plants, you can see which parts of the world we have been active in. I guess many of you in the audience will know this. Heavy industries is widely spread around the world, and therefore we have quite a lot of countries and references that we have worked with. All the industries that we serve is power industry, waste to energy, steel plants, as I'll be talking today, cement making and limestone, lead refineries, zinc refineries, copper smelters, so all non-ferrous, and even the glass industry. All these industries have a similar problem. They have hot gases that have a swirl, so they're not easy to measure. They have a spin or they have a stratification in them. They have dust in them, and therefore they also have very short measurement sections very often. Therefore, they are very hard to measure. One of the main applications that we started with in the steel industry was the measurement of dedusting systems. Many people know that dedusting is a huge energy consumption and a huge energy drain in the plant. And it doesn't matter if it's primary or secondary dedusting systems, they all have in common that usually the flow of the dust and fumes is not measured accurately. And that leads to the fact that very often the fan is not operated in an ideal operation point. Now, everybody of you know, of course, that fan power is a big energy drain. So many fans have problems to be operated at their optimum setting. That's very common in the power industry, cement industry, as it is in the steel industry. If you look at the middle of this picture, you can see the typical fan power curve. And for many new fans, this curve is highly nonlinear, especially if you're using a variable frequency drive. So finding the right set point for the fan by measuring the flow and also by measuring the dust load that goes out these dedusting systems allows for a lower flow set point. And if you have a variable frequency drive fan, then reducing the set point by just say 10% can give you over 20, sometimes even over 25% lower fan power consumption. So looking at fan is one thing, and that has been a major source of our work over the past 25 years. Now, we have done this also with quite a few sites of electric arc furnaces. And here, clients very often used our sensor further downstream where the gas is not so hot. So let's say 500, 600, 700 degrees Celsius, but not warmer than that, because they wanted to know also the exact flow out of their electric arc furnace. And here, many clients came up with the idea of wanting to place the measurement closer to the process. They wanted to measure very close to the electric arc furnace at much higher temperatures. So this led us to the point where we thought to ourselves, how can we provide a measurement that measures up to 2000 degrees Celsius hot gas on the electric arc furnace outlet? So you can see here a little cross section, primary, secondary dedusting, stack flow, all easy. But the point down there on the right hand, the fourth hole, that's usually the hard point to measure. And that's the main interest of people today when they want to optimize an electric arc furnace or optimize a converter. Same thing here, big interest to measure directly on the converter outlet. Very often on these ducts, you have water-cooled ducts because of the hot fumes. You can see on the right-hand side, difficult installation location with only a very small access hole to the process. So how can this be done? How can we measure gas flow out of a converter and out of an electric arc furnace? The key here is our correlation measurement that we have been using for 25 years in many gas flows. The measurement principle is twofold. First of all, you generate a signal. You generate a signal from the process. This signal is usually a random signal. It's a time signature of the clouds of particles that fly by one measurement sensor. For example, you can measure the electrostatic charge of a cloud that is passing by your sensor. So if there's many clouds passing by this one sensor, you will have a succession of signals on that one sensor. If you now have a second sensor and you make the measurement at the same time, and those sensors are spaced close enough, you will see that the signals are very similar, but they are time shifted. This is the classical correlation measurement that we have been using in many industries. However, for the steel industry, electric arc furnace outlet, the gases are simply too hot to put any sensor inside the gas flow. So this led us to the new sensor that we have here. It's an infrared sensor that looks into the process rather than having any sensing element inside. So this sensor looks purely from the outside. It looks through a small hole and it looks at the light generated inside the duct. Now, infrared light is generated at quite low temperatures already. You can see infrared light at 100 degrees Celsius or even below. And it's generated up to very high temperatures. It's no problem to see infrared light at 2000 degrees Celsius. So these are the two sensors that we have installed. You can see they have a spacer bar in the middle. So we have the two signals now, first and the second, and we are able to correlate those signals to see how fast the gas is traveling through the duct. Let me show you a little bit more detail. Here you can see sensor 1 and sensor 2. You can see that the light emitted from the gas clouds is putting a signal onto our measurement sensor. So we are sensing basically a random signal. Yeah, this random signal comes from the random succession of clouds of gas traveling through the duct. When you look at the signal sensor 1 and sensor 2, you can see that the signals are very similar. You can see with your own eyes. You don't even have to, guess. Now, if you put these signals on top of each other, if they are recorded at the very same time, you will find that they are very similar, but they are time shifted. They're not exactly at the same time. So what you can see here is that there is obviously a time gap between signal 1 and signal 2. If you put that into a cross-correlation filter, this correlation filter will give you a cross-correlation function, which is basically nothing else than shifting the two functions on top of each other until they have the biggest similarity. And that point of biggest similarity, you will see in the correlation function as clear maximum. And the time shift at which you can see the clear maximum is the time of flight of the gas. So what we are doing is we're having a digital measurement of time of flight of the gas. If you now take the distance of the sensors, say 300 millimeters, you divide by the time shift that you measure, you're getting a velocity. So our sensors measure velocity. And if you calculate with temperature and barometric pressure, you will get mass flow of the gas or standardized flow. The correlation measurement has some intrinsic advantages over any other measurement in this field. If you are using a correlation-based measurement, you will get a digital time stamp every second. Every second you will see how fast the gas is flowing through your duct. And the first big advantage is that you are looking into the duct in a straight line. You can see that on the right-hand picture here. Our sensors look into the duct if even up to a few meters. So everything that flies through this sort of optical path is recorded as a signal. And this has a very big advantage because we are now recording the velocity as a vector. The distance that we assume in our calculation is the distance that's orthogonal or perpendicular to the two sensors. So if there's any swirl component or any stratification, our sensor will not measure that lateral flow. They will only measure the flow in the axis direction of the duct. It's a very big advantage. It had helped us in a lot of applications in stack flow, but in also other in other process, very difficult process measurements in ducts that are very short and so therefore a huge advantage. Of course, the other advantage is that we are measuring digital. We're not measuring analog, which means whenever you see a measurement, you will see that the measurement is accurate. You will never see a drift in this measurement because all we're doing is we're clocking out two signals in a digital time measurement. Yeah. I very often compare this to the old long play record that you used to have in the 70s and 80s as compared to a CD. If a long play record has a scratch, you can hear that because it's an analog conversion. If you have a CD and it has a small scratch, you will hear nothing because it will completely be corrected by the error correction. It's a digital signal recovery. And it's the same thing here. If you have a clear signal, the signal will be accurate and there will be no drift. There will be no zero span correction or whatever. This is very important because many plants have the problem that every other day they have to maintain their system. They have to do this and that. With our system, you will not be able, you will not be required to do that. Here are our measurement properties in a nutshell. Very wide measurement range from 3 meters per second up to over 100 meters per second. Characteristic accuracy and drift stability is the main point here, 100% linearity, and all the other issues that you can find with so many other measurements are not here. So you can now measure the amount of gas going out your EAF. That's the message in a nutshell, and you can do so reliably. We have been doing this in large boiler applications, even with SRL2 certified systems. So we are very well acquainted with safety integrity level instrumentation, all digital, all based on our technology. Now, when we did that, many clients asked us, well, how exactly do you measure on the infrared? Now, we mentioned to them that, of course, measurement infrared is a bit tricky. If you want to measure the correlation well, you have to be able to look at specific wavelengths. Otherwise, you are not able to measure a good correlation. Otherwise, you will not see a good correlation. This is part of our patented technology. Now, the first question then was, if you are looking at wavelengths, can you measure specific elements? And of course we can. We are mainly looking at the wavelength of CO2, but also looking at CO or water, vapor, or NOx or CH4 is no problem. So basically what our sensors are doing, they are looking at specific wavelengths. We can look how much velocity the gas has, but at the same time, we can also measure the content of certain constituents. So we can measure the content of CO2. We can measure the content of CO or H2O. So if you now put our instrumentation on your furnace, you will automatically get all these constituents with a velocity, and you can use that to optimize your process. Here's how the system looks like. You have a main panel. You have the two sensors there for velocity, and then for each constituent, you have a separate sensor. So if you want to measure velocity, CO2 and CO, you're looking at 4 sensors. If you want to add H2O, maybe there's 1 or 2 more sensors. We hope to be able to get the temperature out of the process as well, out of the sensors that we are already using. So we believe that including temperature, we'll be looking at 5 to 6 sensors that you can position on the outside of your 4th hole. This is how it's all mounted. So you can see the electric arc furnace on the right-hand side, and then right behind the air gap, you can mount our sensors. Our sensors can measure very well through cold air. And that is simply because they're not measuring transmission, they are measuring emission of light. So if you put our sensors right downstream of your post-combustion air gap, they will still see the CO and the CO2 very well, because they are looking right through the cold gas onto those constituents. So this is a typical example of how our sensors are installed. This is a water-cooled duct, and this water-cooled duct has a mounting plate where our sensors are mounted. Please remember, nothing of our sensor will reach into the process. Yeah, we're all only outside the process. So also the alignment of our sensors is not very critical. If our sensors are aligned a little bit in a little bit of an angle, it doesn't really matter to our measurement values. Very simple to install and also very low in maintenance. All of our sensors have cooling air or cooling nitrogen through the housing up to the front of the sensor, where we have a seal air cap that prevents any dirt from getting into our sensor. So our seal air gap allows us to use the sensor without getting dirty or getting some problems with dirt and dust. The sensors have been running for many, many weeks now in many plants, and there's no need to take them out or to clean them on a regular basis. Here you can see a typical trace of several heat cycles that have been going on. The blue line is basically the velocity that we're seeing on the outlet of the 4th hole, the digital velocity measurement. And the red line is the CO2 that you can see coming off the heat cycle. So this is something that your operators could see on a screen. Our response time is usually 1 second. So you have a real-time measurement of our system. There are also other systems on the market. We are aware of that. There are extractive systems, which are, in many cases, we have found to be quite difficult in maintaining well. There are also laser-based systems out there. The laser-based systems usually have 2 disadvantages to look at. The first one is that a laser cannot protrude through a very long path if there's a lot of dirt and dust. So you need to put the laser fairly close to each other, and that means that you can only look at a small gap. especially the laser is not very good at looking through cold air. This is one of the main advantages of our system. We can look through the cold air gap, and therefore we don't have to put anything inside the duct. We don't need any inside duct things, so we can just look from the outside. The other disadvantage of the laser, of course, is the misalignment. The two laser heads have to look at each other. Our system is only from one side. The PROMECON system looks only from one side and does not look into the process, only from the outside. Very simple, very easy. Here you can see a typical comparison between the laser system and our system over a heat cycle. You can see very well that the traces are very similar. Our signal was not smoothed or massaged in any way. Therefore, it's a raw signal. It's a bit more noisy, but it can be used very well to control a process. And also what you can see on the laser-based signal down below is that there are several points in the measurement where the laser drops out because maybe of alignment issues or whatever. So there are always these gaps that make it hard for the operator to run the process smoothly. And our system, by definition, do not have these dropouts. So much easier, much more reliable. Here again, you can see a typical trace of the infrared measurement of velocity based on the CO2 constituents of the gas. So it's a very good application for high temperature. It's very well suited for EAFs and BOFs. You can measure the mass energy balance with it. You can see also how to optimize your burners in the EAF. You can optimize your blow cycle in the BOF. I don't think I have to tell you all the advantages that you can derive from this in your process, but we believe that the payback of the system in any EAF plant will be very, very quick. And therefore, we think that there will be a lot of interest generated in the industry with this system. I will be looking forward to the Q&A session later on, and I will be happy to answer any and all of your questions. So hopefully we'll see you in a few minutes and I can then take your questions. So enjoy your conference, and I hope that I can answer all your questions later, and let's see you then.